You know, every single business out there is sitting on what's basically a gold mine of data. But here's the thing. The most valuable stuff isn't the answers to questions you already have. It's the answers to questions you haven't even thought to ask yet. So today, we're going to dive into the architecture of unsupervised discovery, the algorithms that find these incredibly profitable hidden patterns in your data, all without you having to tell them what to look for. So here's the game plan. First, we're going to get a handle on the core problem. What do you do with data that has no labels? Then we'll check out the classic toolkit, kind of the old-school hammers and screwdrivers of data science. We'll see where they fall short, which leads us right into the modern revolution and the super-powered tools we have today. And the real magic? Well, that happens when we combine them into what we call the ultimate power pipeline. Finally, we'll connect all that tech stuff to what really matters, real-world business impact. Let's jump in. All right, let's start with the fundamental challenge. Most data doesn't come in neat little packages with labels telling you what everything is. It's just data. It's raw, it's unlabeled, and it is absolutely full of hidden potential. And this really gets us to the heart of this entire field. See, in supervised learning, you have a target, right? You want to predict house prices or figure out if an email is spam. The answers are already in your training data. But here, there are no predefined answers. It is pure exploration.
So wait, you're saying it's like someone hands you an entire library where none of the books have titles, they're not sorted by genre, and you somehow have to figure out the entire organization system just from scratch?
That's it. That is the perfect analogy. You have to let the books, the data points themselves, tell you how they relate to each other. And that's really what we're talking about when we say unsupervised learning. These algorithms are designed to find that hidden structure for you. The goal isn't prediction, it's discovery. The data itself tells you which customers are secretly alike, or which sensor reading is the weird one out that's signaling a future engine failure. The data is speaking, and these algorithms are how we finally learn to listen. So to kick off that discovery process, data scientists have had a classic toolkit for a long, long time. These are the foundational algorithms, the real workhorses that have been powering the industry for decades. The most famous of these, by far, is K-Means clustering. It's incredibly fast and really efficient. Think of it this way. Imagine you've got a huge room full of people. Those are your data points. Your job is to set up a certain number of Wi-Fi routers. Let's say K equals 3. You place these routers, which we call centroids, somewhere in the room. Then every single person connects to whichever router is closest to them. K-Means then just keeps moving the routers to the center of their little groups, over and over, until the groups are as tight and distinct as possible. Okay, that makes sense. It's fast, it's simple. But looking at this slide here, I'm seeing a few red flags. It says the geometry is biased toward globular, spherical shapes. What happens when your customer groups don't look like neat little circles? You know, what if a group is long and thin or shaped like a donut or something? And it says it's sensitive to outliers. That seems like a big problem.
You've absolutely nailed it. Those are the exact limitations. K-means will literally force every single point into a cluster, even if it's a total outlier that doesn't belong anywhere. And yeah, it really struggles with anything that isn't roughly round, and that's exactly why the classic toolkit has more than just one.
Right, for another classic problem, when your data is just way too complex, we have something called principal component analysis, or PCA. The best way to think about this is to imagine you have a really complex 3D object, like a chair. If you shine a light on it, you create a 2D shadow. Well, PCA is like finding the absolute perfect angle to shine that light, so the shadow it creates is as informative as possible, capturing the most important features of the chair's shape. It takes hundreds of features or dimensions and squishes them down into just the vital few that explain the most. So how does it find that perfect shadow? Well, in simple terms, first it puts all your data features on the same scale, so nothing is overrepresented. Then it finds the most important directions of variation in your data. These are the principal components. Just think of it like finding the length, width, and height of the data cloud. Finally, it just keeps the most important dimensions, like length and width, and gets rid of the rest, giving you a much simpler but still very informative picture. Okay, I get PCA for simplifying things, but wait a minute, the sources mention a major weakness. It only works for linear relationships. It basically assumes everything can be described with straight lines. But real-world data, I mean customer behavior, financial markets, biological systems, it's almost never that simple. It's messy, it's complex, it's non-linear. So what happens when the classic tools just can't cut it?
That is precisely the question that drove this modern revolution in data science. The classic tools are great, but modern data just demanded a whole new level of sophistication.
So to solve that problem of non-spherical clusters that totally stumped K-means, we have HDBSCAN. Now this algorithm is incredible. It can find clusters of varying densities and any shape imaginable. A great way to think about it is like a satellite mapping a new continent. It doesn't just assume all the cities are perfect circles. No, it identifies the dense urban cores, the sprawling suburbs, and the sparse rural areas, and it traces their actual irregular shapes. And this is crucial. It also recognizes the empty space between them as noise, instead of forcing everything into a category it doesn't belong in.
And to answer your challenge about PCA and its straight line problem, we now have UMAP. If PCA is about creating the best possible shadow, UMAP is more like carefully uncoiling a tangled up spring and laying it flat on a table. It preserves not just the local connections, which parts of the spring we're touching, but also the global structure, the overall shape and length of the spring itself. It's a nonlinear method built specifically for the complex, twisted shapes that modern data almost always takes. And this slide really shows why UMAP has taken the data world by storm. When you compare it to older nonlinear methods like TSNE, it's not just faster. We are talking about minutes of processing time instead of hours on large data sets. It also does a much better job of preserving the big picture global structure. See, TSNE is great at showing you tight local neighborhoods, but it often completely shatters the relationships between those neighborhoods. UMAP gives you both, the fine-grained local detail and the global context. Okay, now for the real breakthrough. These modern tools? They're powerful on their own, for sure. But the true revolution, the real game changer, comes when we stop using them in isolation and start using them together in a very specific intelligent sequence. This is what we call the ultimate power pipeline for finding hidden insights. Step 1 is all about taming the complexity. You feed your messy, high-dimensional data straight into UMAP. This is that uncoiling the spring step we talked about. UMAP intelligently untangles all those features into a much simpler space. Think 5 or 10 dimensions instead of hundreds, while carefully preserving the essential structure of the data. Then, once you have that simplified, cleaner data, you apply HDBSCAN to it. And this works so well because of something called the curse of dimensionality. Basically, when you have too many features, the whole concept of distance between data points breaks down, and everything starts to look equally far apart. It's like trying to find clusters in a dense fog. By letting UMAP burn off that fog first, we give HDBSCAN this crystal clear landscape where it can easily spot the true complex shaped clusters. And the result? It's not just a little better. Research shows this two-step pipeline delivers a 2 to 3 times improvement in clustering quality on complex data compared to just trying to cluster the raw, high-dimensional data directly. That is a massive leap in performance. Okay, hold on. A 2 to 3x improvement in a technical metric. That's impressive for data scientists. I get it. But let's bring this back down to earth. How does this actually make a business money or save it from some kind of risk? Why does a CEO or a marketing director care about a UMAP HDBSCAN pipeline? That's the million-dollar question, isn't it? Let's look at this slide on marketing impact, because this is exactly where discovery enables decisions. An unsupervised model might discover a hidden cluster of customers who browse all your high-end products, but they only ever buy during a sale. That's an insight. The decision is to create a targeted email campaign specifically for them, which then leads to a 10 to 20% boost in ROI. Or it identifies a group that's showing early signs of churn, allowing you to send a proactive retention offer. This isn't just exploring data for fun. It's a direct line to measurable business outcomes. And it is absolutely not just marketing. In finance, these techniques are spotting subtle fraud rings that don't fit any known patterns. In manufacturing, they're analyzing sensor data from a jet engine to detect a faint, anomalous vibration that signals a potential failure long before it becomes critical. This is all about proactive risk mitigation and huge operational efficiencies, all driven by unsupervised discovery. Which brings us to what I think is the single most important takeaway from all of this. This quote says it all, really. The technical work of finding the clusters, that's just the starting point. The real value is unlocked when you frame that output to answer a business question and enable a specific action. The question should never be, what clusters are in our data? It has to be, what decisions can these clusters help us make? And this leads us to our final forward-looking question. You see, tools like PCA are transparent. You can actually trace back how they made a decision. But UMAP and HDBSCAN, they're more like black boxes. They give you incredibly accurate results, but it can be really hard to explain exactly why they grouped things the way they did. So,
As these powerful but pretty opaque tools become standard in high-stakes fields like finance and medicine, the critical challenge is going to be balancing this incredible power of discovery with the regulatory and ethical need to understand and explain our models. And that right there is a conversation that is only just beginning.